Hydrogen and its compounds. You know, hydrogen is placed in the first period as well as in the seventh period, along with alkali metals lithium, sodium, potassium, etc., and fluorine, chlorine, bromine, iodine. In Mendeleev's classification, hydrogen is placed both in the first and the seventh periods because hydrogen resemblances some of the properties of alkali metals as well as some of the properties of halogens. Like alkali metals form Li plus, Na plus, K plus, hydrogen also forms H plus, and like halogens are F2, Cl2, Br2. Hydrogen is also diatomic gas. It is a gas, it is diatomic. So it has some similarities along with the alkali metals and along with the halogens also. Therefore, in the modern periodic table, hydrogen is neither placed in the first group or the seventh group. It is kept separately. Hydrogen belongs to a block of itself. You can say it is H block. And indeed, hydrogen has some unique properties, and let us discuss some of the compounds of hydrogen. Water. Water, you know, is a very, very, very important compound of what? Hydrogen. And water. Any harm or benefit we derive through water is due to soluble substances only. That is, only when a substance is soluble in water, it can give us any benefit or harm. For example, if glucose is not soluble in water, there is no point in adding water and glucose and then drinking, because glucose remains at the bottom and you don't get any energy. Okay, therefore, if a substance is not soluble, once again it cannot cause even any damage to the body. Therefore, any harm or benefit we derive through water is due to soluble substances only. Assuming potassium cyanide is not soluble in water, say, if it is not soluble, you can safely add potassium cyanide to water and drink it, because potassium cyanide doesn't produce potassium ions and cyanide ions will not be able to interact with the human system. Therefore, any harm or benefit we derive through water, we get through water, is due to soluble substances only. Basing on this idea, we look at some of the properties water can have. Look here. Hard water. Hard water. Water that does not give lather, froth, foam, all three mean the same. Lather or froth or foam. Water that does not give lather, froth or foam with water is said to be hard water. So, hard water does not give lather, froth, foam with soap. With soap. When soap is added, you don't get any froth. Water that does not give lather, froth, foam with soap is called hard water. Now, who is responsible for this hardness? Let us see. Bicarbonates, sulfates and chlorides of calcium and magnesium cause hardness. These are responsible for hardness. How many salts are they? Calcium bicarbonate, calcium sulfate, calcium chloride, magnesium bicarbonate, magnesium sulfate, magnesium chloride. Put together, there are 6 salts. So, any of these present in water renders water hard. Water becomes hard water. Out of which bicarbonates cause temporary hardness, sulfates and chlorides cause permanent hardness. What do you mean by temporary hardness? Doesn't mean that it will be removed in 5 minutes. It is only temporary. It is not like that. Temporary means which can be removed easily removable. The hardness can be removed easily. Permanent doesn't mean permanent, it remains forever. Removing permanent hardness is slightly difficult, more difficult than temporary hardness. Listen, what do they do when they are in water? Let us see. Dirt which deposits on cloth. Suppose if there is a dust can be easily removed, it can be dusted off. If there is some sand deposits, they can be removed easily on cloth. But what is dirt? Dirt is oily deposits. Dirty cloth will have some oil on that. So, dirt and water, that is oil and water, do not mix with each other. Oil and water do not mix with each other. It's easy to understand why not. Because oil is non-polar. Water is polar. So, between molecules of water, there is electrostatic attraction. Hydrogen bond, you know. Between molecules of water, what exists is a hydrogen bond. Minus delta, plus delta. So, to separate water molecules, you need to have charge. Suppose if there is an Na plus ion, that Na plus will attract this O minus and Cl minus will attract this H plus. So, when NaCl is added, Na plus attracts O minus or O minus attracts Na plus, H plus attracts Cl minus. These two are separated. Suppose you have Na plus and Cl minus here. What happens? O minus moves towards Na plus and H plus moves towards Cl minus, and these two water molecules are separated. So, to separate electrostatic attraction, you need charge. And so, what is oil? Oil is an organic compound. It is a tristearate of a glycerol. It is a triester, glycerol triester, a heavy molecule roughly containing 50 carbons, oil. So, most of the oils contain, oil or fat, they contain long chain fatty acids. Long chain fatty acids like stearic acid, palmitic acid, oleic acid. For example, stearic acid is this CH3 CH2 17 times COOH. This is stearic acid. When glycerol reacts with this stearic acid, and glycerol has 3 OH groups. Glycerol CH2OH, CHOH, CH2OH, and these long chain fatty acids RCOOH, each containing roughly 17-18 carbons, RCOOH. What happens? HOH. what you get is called ester. Alcohol plus acid, what you get is called an ester, and this is in fact a triester because you have 3 ester molecules. 3 alcohols, 3 acids are combining. Therefore, this triester of fatty triester of glycerol, glycerol is oil or fat, collectively called, of course, lipids. They are called lipids. Oil or fat, which is called lipids. So, what exists between 2 molecules of glycerol? I mean, this oil or fat, which is a heavy molecule, only van der Waal attraction. The attraction here is van der Waal, and the attraction in water is electrostatic. This is electrostatic. So, oil does not have the electrostatic attraction to separate water, nor water has the mass to separate van der Waal attraction. We discussed in intermolecular forces, only mass, a heavy one can only a heavy one can separate this. To separate 2 oil molecules, you need a heavy molecule which will be able to attract another heavy one, heavy. So, neither water has the mass nor oil has the electrostatic attraction charge to separate water molecules. Therefore, oil and water do not mix with each other. So, what happens? A third person will make them mix. A third person will hold both of them. The third person is called an emulsifying agent. What will this emulsifying agent do? He will hold on to oil on one hand and water with another hand. Oil means, in our case, it is dirt. We are talking about washing clothes using soap, and soap acts as emulsifying agent. So, what will soap do? Soap holds on to water on one hand and oil on the other. Soap holding water and oil, that is dirt. So, now all these 3 are collective, all these 3 are bonded. There is a bond between dirt and soap and water. So, there is an indirect bond between dirt and water. So, water is fluid, water keeps on moving. When water moves, behind water you have soap and behind soap you have dirt. What goes out is dirty soap water, and that dirty soap bubbles, they are called froth or lather or foam. This is froth. So, when is this froth formed? Only when soap, water and this dirt all 3 mix, then only this froth is formed, and along with this froth, dirt is washed out. So, soap helps in doing this. We will see how soap will be able to do that. That is not a big thing. Now, so this dirty soap water, this is called froth. So, in hard water, this froth is not formed, means these 3 are unable to combine. Why are they unable to combine? We already know dirt and water, they in any case cannot combine. Oil and water cannot combine. This soap is helping in combining them. In hard water, what might be happening? The soap is disappearing. I don't know what is happening to soap, but the soap is not present in hard water. Even though you add soap, it is not present in hard water. What exactly happens to that, we will see. First of all, let us look at soap. For example, let us say it is sodium stearate. It is only one of the examples. Sodium stearate is soap. Sodium stearate, CH3, CH2, 17 times COO minus Na plus. Okay, let this be soap. One of the examples of soap. Sodium stearate, palmitate, oleate, there are many things. And this stearate ion, you look at the peculiarity, CH3, CH2, because it is a very 17 times COO minus, it has, on one hand, it has a charge, it is charged. With this charge, it will attract the positive charges of water, HOH, H plus delta, plus delta. This O minus will attract to, and this is called hydrophilic end. What do you mean by hydrophilic end? One of the extreme one extreme which likes water, hydrophilic, water liking part of soap. This is the water liking part of soap. And on the other hand, since you have many carbons here, it has the mass, it can hold on to oil which has van der Waal. So soap has both van der Waal and charge, both mass and charge. Therefore, this mass is attracting non-polar substances, non-polar attraction, polar attractions. Means soap, that stearate ion is a very long chain molecule which has both the hands, and this is called hydrophobic end. Hydrophobic end. Now, so it is not actually just one stearate ion doing this. When many stearate ions meet in water, two stearate ions meet head on, say CH3, CH2, COO minus, and another COO minus. Suppose they happen to meet like this, CH2, CH3. When these two negative charges, when they oppose each other, what will happen? Naturally, they repel. And when they repel, their opposite ends attract. These two repel, no doubt, but the opposite ends start accumulating. CH2, COO minus, another CH3, COO minus, another CH3, COO minus, another CH3, COO minus. Nearly 60-70 of them gather like this. 60 to 70. 60-70 stearate ions form a big group which is called a micelle. This is called soap micelle. So it is not exactly one stearate ion that is attracting, a group of stearate ions which may contain 60 to 70 stearate ions like this. Now this dirt is attracted to the center. Dirt goes to the center, and water is on the periphery. Water is on the circumference periphery. So now, since water has hydrogen bonding, you see a thin film of thin layer of water, and that's why you see that as a bubble. So water is scattered, the negative charges are scattered because of repulsion. Why are the negative charges like this, like spokes of a wheel to different directions? Because of repulsion. And why are the opposite ends, these ends, hydrophobic ends, these ends, why did they come close? Because of van der Waal attraction. You have attraction here and repulsion here, and mass here, charge here. Mass is there at the center of the bubble. Mass is concentrated at the center of the bubble, and charge is towards the end of the bubble. Therefore, water is at the end, and now here you have dirt got attracted. Means literally this group of stearate ions literally pulls dirt out of cloth. Whatever dirt is there, it is literally pulling it out using force. The dirt is pulled out. Okay. So this is the action of soap. So now what exactly is soap? Stearate ion. So when sodium stearate is added to water, that should be soluble first and produce stearate ions. Then stearate ions repel each other, and then they form this group called micelle. Okay. Hard water containing calcium and magnesium ions. Hard water which contains calcium and magnesium ions, when added to stearate ions, sodium stearate or potassium stearate, there are many. You can use any long chain fatty acid. I repeat, you need to have a minimum of 12 to 17 carbons, because it should be heavy enough. When they accumulate, you should get some mass, and that mass only will be able to attract oil. Therefore, hard water stearate ion, this calcium stearate is formed. You may get it out. What if calcium stearate is formed? Formed means stearate ions are precipitated. Soap, now stearate ions, they are no longer in water. When you add soap to hot water, all the soap gets precipitated and forms a scum, what you call scum, that useless material is formed. So, stearate ions, when they are present in water, they are any good to us, but when they are precipitated, they are not good. Therefore, calcium stearate, magnesium stearate, both of them, because they are not soluble in water, they don't produce stearate ions. Once stearate ions are not there, soap is not there. So, even though you have added stearate, that is precipitated, whereas in normal water, stearate ion is soluble and then okay. So why do we mention only those 6 salts responsible? Look here. Why doesn't potassium chloride cause hardness? KCl doesn't cause hardness. Why not? KCl doesn't cause hardness. Calcium chloride causes hardness, but KCl doesn't cause hardness. Why? You know, K plus ions do not precipitate stearate. Potassium stearate is soluble. Potassium stearate is soluble in water. Therefore, there is no harm with potassium. And why didn't I mention calcium carbonate or magnesium carbonate? Calcium carbonate doesn't cause hardness. Doesn't cause hardness. Why doesn't that cause hardness? Calcium carbonate cannot cause hardness because calcium carbonate itself is not soluble because it is insoluble. Calcium carbonate doesn't produce calcium ions which might kill stearate ions. So, you don't have calcium ions here. So, once again, if a substance is insoluble, that will not damage us. Calcium carbonate doesn't cause hardness. Calcium bicarbonate causes. Okay. So, calcium. Then, calcium oxalate. Calcium oxalate doesn't cause hardness. I didn't mention calcium oxalate. Why not? Calcium oxalate is soluble. Calcium oxalate produces calcium ions, and calcium ions eventually will precipitate stearate. But why didn't we mention calcium oxalate? That calcium oxalate is not present in water bodies. It should be in nature first. If it is present in water bodies, then that will react with soap and may or may not precipitate. So, what are the 3 qualities necessary to cause hardness? Naturally occurring, it should be present in nature. Naturally occurring soluble substances. It should occur in nature, it should be soluble, naturally occurring soluble substances that precipitate stearate ions. Soluble substances which produce ions that precipitate stearate ions cause hardness. So, there are 3 conditions. KCl doesn't cause hardness because K plus doesn't precipitate stearate ions. CaCO3 doesn't cause hardness because it is not soluble. Calcium oxalate doesn't cause hardness because it is not present in nature. It is not naturally, it is not in nature, it is not soluble, it doesn't precipitate stearate ions. So, a substance which produces stearate ions or which produces ions that precipitate stearate ions, I repeat, it should produce ions, those who precipitate stearate ions only cause hardness. So, only those 6 salts you can claim to be causing hardness. Okay? Now, removal of temporary hardness. A simple procedure. Temporary hardness, you know, because of calcium bicarbonate and magnesium bicarbonate. Temporary hardness because of calcium bicarbonate and magnesium bicarbonate. So, you don't need to do anything, simply heat that. By boiling water, what will happen? This calcium carbonate is converted to calcium bicarbonate is converted to calcium carbonate, and calcium ions are precipitated. So now you don't have the dangerous calcium ions. Calcium bicarbonate, there are calcium ions, but when that is heated, calcium ions themselves are precipitated. So calcium carbonate is insoluble in water. So by boiling hot water, what happens? By boiling hot water, you can remove hardness. So temporary. So heating is one technique, but you can't do that in a long scale. In industry, you need lots of water, and you can't go on heating so much of water. So what will happen once again? So removal of temporary hardness. There is another method. It is the Clark's process. Clark's process. By adding calculated amount of slaked lime. Calculated amount of slaked lime. Calculated quantity of slaked lime. What is this calculated quantity? Look here. Calculated amount of slaked lime. You have calcium bicarbonate. I am adding calcium hydroxide, which is called slaked lime. It is a semi-solid. Slaked lime is a semi-solid. You add water to quicklime the powder. When you add water, you get a semi-solid slaked lime. Now, once again, what happens? Calcium carbonate gets precipitated, CaCO3. This Ca and CO3, this is Ca and again in CO3, 2 CaCO3. You have 2 hydrogens here and 2 OH here. You get 2 H2O. So now hardness is gone. How? Calcium ions are precipitated. So in both the processes, we have precipitated calcium ions. Here is a warning. You should add calculated amount. Means if you take 1 mole of this, you have to take only exactly 1 mole. What happens when excess is taken? When excess is taken, excess makes it permanent hardness. Excess slaked lime makes hardness permanent. Temporary becomes permanent. Why? When you add excess calcium ions, what are you doing? You are precipitating calcium ions as well as bicarbonate ions, and since you have taken excess this is over, calcium bicarbonate is over. You have added excess of this, means only calcium hydroxide is there in water. So earlier in temporary hot water, you have both calcium ions and bicarbonate ions. Temporary hot water contains both calcium ions and bicarbonate ions. Temporary. So what can you do? By heating this, what happens? Bicarbonate is converted to carbonate, and this carbonate will precipitate calcium. Calcium carbonate is precipitated. So when bicarbonate ions are present, it was easy for me to convert them to carbonate and then make calcium ions precipitate. To precipitate calcium ions. So what are you doing by adding excess? All calcium bicarbonate is gone, and now I have only calcium ions in water, no bicarbonate ions. So earlier when bicarbonate was there, by heating bicarbonate I got carbonate precipitates calcium. Now, so calcium ions are dangerous in the sense calcium ions cause hardness. Calcium ions are dangerous, but less dangerous in presence of bicarbonate ions, because when heated, calcium gets precipitated. So you should not add excess. So excess, what will it make? Now you only have calcium ions. Now you need a different procedure to remove that hardness. So removal of temporary hardness, boiling. So what is it you should do? Precipitate calcium ions. What is the ultimate goal? Precipitate calcium ions. Now, permitite process. This is for permanent hardness, removal of permanent hardness. Removal of permanent hardness. Permitite's process. Na2Al2Si2O8XH2O. This is sodium aluminum orthosilicate. This is a naturally occurring earthy formation, something like stone. Sodium aluminum orthosilicate. So, this sodium aluminum orthosilicate is called zeolite. It is naturally occurring, but this can also be prepared artificially by heating these three things: sodium carbonate washing soda, Al2O3 alumina, and SiO2 n times silica sand. By heating all these three, you get zeolite, but in an artificial manner. This is called artificially made zeolite. Artificial zeolite. All right. This is called permitite. So, you get it naturally also, you get it manufacture it also. Once you manufacture, in fact, you can even recycle that, you can use it, reuse it again many times. So, this zeolite. So, hard water containing calcium magnesium ions, from hard water. When permitite is added, what is permitite? Na2, Al2, Si2O8. I simply call it Z. Na2, Al2, Si2O8. I am calling it Z. Na2Z. What happens? CaZ is formed. Don't mistake that word. CaZ is formed means calcium ions are precipitated. So, what is the cause of celebration? Calcium ions are dead. Now, hardness is gone. So, whenever you hear such a word in chemistry, CaZ is formed, what you think is, okay, earlier Na2Z was there, now CaZ is there. What is the difference? There is a lot of difference. Earlier, calcium ions, sodium ions, everything were there. Now, calcium ions got precipitated. So, this downward arrow is very important in this chapter. Be careful with that. So, calcium ions are precipitated. So, if they are not soluble, if they are not present in water, they can't cause any damage. So, the first sentence once again, any harm or benefit we derive through water is only through soluble substances. If a substance is not soluble, it can't cause any damage to us. Now, Calgon's process. Calgon, of course, is the trade name of sodium hexametaphosphate. Sodium hexametaphosphate. NaPO3 6 times. Metaphosphoric acid is HPO3, metaphosphate PO3. Hexa, sodium hexametaphosphate, NaPO3 6 times. Therefore, NaPO. So, you add this to water, Calgon. Calcium magnesium ions, which are present in hard water. I am adding Calgon. Na2, Na4PO3 6 times. Now, what happens is you get CaNa4PO3 6 times, and once again is insoluble in water. Calcium ions are precipitated. So, this calcium adsorbs. You can say either this is complex formation, or adsorption. Can be anything, any of the word, complex formation or adsorption. So, this is how we remove permanent hardness. Now, let us see measurement of hardness. Degree of hardness. measurement of hardness. ppm means parts per million parts. Parts per million parts. What do you mean by that? As it is, it doesn't mean anything. You have to mention which parts out of which parts. For example, 1,000 people, that part is people, 1,000 people per million people. A population of 1,000 in a population of million, a total of million people. So, replace this part with anything. Okay, you can say 1,000 tube lights per million tube lights. So, ppm as it is has no meaning. ppm by mass or ppm by weight means, ppm by weight means x ppm means x gram per million gram. X gram per million gram. So, what we should now do is, you have to measure how much of that salt is present in million gram. How many grams are present in million gram? Okay, ppm, for which there is a simple technique. 10 power 6 gram, which is also million gram, or 1000 kg water, 10 power 6 gram or million gram or 1000 kg water. All three are one and the same. 1000 kilogram, 10 power 6 gram. If it contains x gram calcium carbonate equivalents, don't read that as x gram equivalents of calcium carbonate. I am not talking about the mass of calcium carbonate present, because you know calcium carbonate cannot be present in water. It is x gram calcium carbonate equivalents, means whatever salt, the equivalents of the salt and the calcium carbonate equivalents are equal. Why is it measured in calcium carbonate equivalents? Because there are 6 salts that can cause hardness. Sometimes you may have more than 1 or 2 salts there, more than 1, more than 2, more than 3 salts can be there. Therefore, you cannot express hardness in terms of a bicarbonate, in terms of sulfate, or in terms of someone in particular. Therefore, it is collectively mentioned. So, you convert everything to calcium carbonate equivalents now. So, x gram calcium carbonate equivalents, hardness is said to be x ppm by mass. Or simply, when the number is, the mass of water given is in grams, you just go to 1 kilogram. 1 kilogram water, if it contains y milligram calcium carbonate equivalents. They were grams and grams, and now kilogram and milligram. Kilogram and milligram. So, once again ratio kilo versus milli is 10 power 6. So, 1 kilogram contains y milligram calcium carbonate equivalents. The hardness is said to be y ppm. So, what you need to do is find the equivalents of a salt and find the mass of that many equivalents of calcium carbonate. Suppose if 1 equivalent of calcium bicarbonate present, you call it 100 in terms of calcium carbonate. Now, first of all, let us look at the molecular weights of the 6 salts. Calcium bicarbonate 162. Corresponding magnesium salt will be 16 less than that. 4024, atomic weights of calcium and magnesium are 4024. So, corresponding magnesium bicarbonate will be 16 less, 146. Calcium sulfate 136. Corresponding magnesium salt, magnesium sulfate 16 less, 120. Calcium chloride 111. corresponding magnesium chloride 95. So any of these is equivalent to 100 when it comes to calcium carbonate. So if you say 162 gram by calcium bicarbonate, that is, if the same equivalence of calcium carbonate is present, it is 100 gram. 162 grams will be called 100. 146 will be called 100. 136 of calcium sulfate will be called 100. So magnesium sulfate, if 120 grams are present, you call it 100. If 60 grams are present, you just call it 50. So the equivalence of magnesium sulfate will be the equivalence of calcium carbonate and find the mass. So x gram calcium carbonate equivalence after converting the language to calcium bicarbonate. Now let us simply do many problems. Mass of water, mass of the salt. I am not using any formula, I am just using the definition and then trying to apply. Mass of the salt. Mass of calcium carbonate equivalents. And hardness in ppm. Look here. First problem. 500 kilogram water contains 73 gram magnesium bicarbonate. So these two are given. The data is rounded off. Now you have to find these two. What is the question? 500 kilogram water contains 73 gram magnesium bicarbonate. What is the hardness? 500 kilograms contains 73. The first thing you should do is you convert that to calcium carbonate equivalents. 146 is equivalent to 100, 73 is equal to 50. Here it is 50 grams. So this is what I am finding out. So don't round that off. Whatever is given is rounded off so that you know what is the data and what is the question. What is the question and what is it you have to find out. These two you have to find. So first one, what is the first step? First step, you change the language from bicarbonate to carbonate. Second one, apply the definition. Just apply the definition. That is 500 kilograms contain 50, but according to definition, 1000 kilogram how many? 550, 1000 how many? 100. Therefore 100 ppm. Very simple. Second question. 250 gram water. 250 gram water contains 12 milligram magnesium sulfate. Find hardness. 12 milligram magnesium sulfate. So it is 12 milligram. 120 is equal to 100. 12 is equal to 10. It will be 10 milligram. 10 milligram. But this 10 milligram and 12 milligram, they are present in 250 grams water. 250 gram. But according to the definition, 1000 gram how much? 250, 10, 1000, 40. 40 ppm. Like this you can solve any number of problems just in one line. Don't need to have a question dictated and have 4 options at the end. Now, 3. (250 kg water). Hardness is 200 ppm. And the hardness is due to, say, calcium bicarbonate. Find the mass of, you find this. 250 kilogram, 200 ppm. What do you mean by 200 ppm? 1000 kilogram, 200 grams. 1000 kilogram, 200 gram, that to calcium carbonate equivalents. In 1000 kilogram, if you have 200 grams of calcium carbonate equivalents, you call it 200 ppm. What is the definition? 1000 kg water contains 1000 kg water. 1000 kg water contains X gram calcium carbonate equivalents. Then the hardness is said to be X ppm. So when the hardness is 200 ppm, then the hardness is 200 ppm. Sorry, X ppm. In this case, X ppm. So 200 ppm means 200 gram calcium carbonate. 200 gram calcium carbonate in 1000 kilogram water. 1000 kilogram, 200 gram. But this is not 1000 kilogram. 1000, 200, 250 how much? 50 gram. But 50 gram calcium carbonate, how much of calcium bicarbonate that is equivalent to? 100, 162, 50, 81. So the mass of calcium bicarbonate present is 81. Without using even paper, pen and formula, you can solve questions like that. So initially it's very difficult, but after practice for 5-10 minutes, you will get concrete command over this concept of hardness of water, measurement of hardness. Just we are finding something in million gram, ppm, that's all. That is measurement of hardness. That's all about hard water.